gas, and plasma, a simple and orderly hierarchy of matter that school children the world over can recite. But what if we could combine the properties of two of these and create a whole new hybrid form of matter that seemingly violates known laws of physics? For example, think of a solid-liquid combination along the lines of the sci-fi classic Terminator 2 Judgment Day. You would theoretically get the crystalline structure of a solid that flows like a liquid, and its possible applications are mind-blowing. And now, it's no longer theoretical. Welcome to Fact Nominal. In today's video, we reveal a stunning leap forward by physicists who've combined what appears to be mutually exclusive properties into an entirely new state of matter, the supersolid. Much like time travel and wormholes, scientists have long theorized the existence, or at least possibilities, of supersolids. In 1957, physicist Eugene Gross predicted this utterly counterintuitive state of matter, which behaves both as a solid and a frictionless liquid simultaneously. In terms of technological capabilities, this was akin to Leonardo da Vinci's 1493 design for the helicopter. Researchers have known for years of superfluid, the result of cooling liquid helium below its boiling point of minus 452 degrees Fahrenheit. This is bizarre in its own right, able to do things other fluids thankfully cannot, such as climb up and over the sides of a container and stay motionless while the container is spun. If you cool any material low enough, it becomes a solid, except for helium. Quantum physicist Warwick Bowen from the University of Queensland explains that it's due to the quirk in quantum mechanics that materials always have a minuscule amount of quantum zero-point energy, even when they're at absolute zero. He says, for helium, that energy is enough to melt the solid. In some sense, quantum mechanics is melting the helium and causing it to be a very different type of fluid. Basically, a superfluid that flows without friction or turbulence, but more on that later. So what exactly is it? As Bowen further notes, we don't 100% understand ourselves. John Beamish, an experimental physicist at the University of Alberta in Edmonton, explains that a normal liquid being spun around in a cup will circulate slower and soon stop when the cup is put down. Not so with a superfluid. As he says, if you set down a cup with liquid circulating around and you come back 10 minutes later, of course it's stopped moving. But if you did that with helium at low temperature and came back 1,000,000 years later, it would still be moving. The supersolid is a combination of the mundane and the esoteric. After all, what's more mundane than a simple solid object? The esoteric is this wonderful quirk of quantum mechanics we call the superfluid. And the strangeness is just getting started. In 2017, MIT researchers hit pay dirt. Physicists initially tried to find supersolids in supercooled helium, which seems logical in that this is where glimpses of superfluids have been seen. But so far, no luck. Then experiments turned to the elements of rubidium and lanthanum, trapping a small number of gaseous atoms and cooling them to only a fraction of a degree above absolute zero, the lowest temperature possible, minus 459.67 degrees Fahrenheit. If your local weather forecast ever calls for this temperature, you should probably leave your faucets running. Researchers took what's called a Bose-Einstein condensate, a special state of matter created in 2001 by Nobel Prize in Physics winning researchers Eric A. Cornell, Wolfgang Ketterle, and Carl E. Wyman, and used lasers to cool it to near absolute zero. There, the physicists played with the interactions of these super cold atoms in this state of quantum weirdness, using the intensely magnetic diprosium-164 to cause clumping together in droplets similar to small bar magnets. The team proceeded to carefully align the balance between long-range magnetic interactions and short-range contact interactions between atoms, says Matthew Norcia, physicist at the Institute for Quantum Research at the University of Innsbruck Optik in Austria. In doing so, the team created a long, one-dimensional tube of droplets that held free-flowing atoms. A 1D supersolid. Norcia explains further. Normally, you would think that each atom would be found in a specific droplet with no way to get between them. However, in the supersolid state, each particle is delocalized across all the droplets, existing simultaneously in each droplet. The result: a mind-altering series of high-density regions, the droplets, that share the same delocalized atoms and enable frictionless flow. To picture a supersolid, consider an ice cube immersed in liquid water, with frictionless flow of the water through the cube, explains Dr. Bruno Leberth-Tolra at Paris North University. Breakthrough number 2 came in 2021 with the formation of systems with multiple rows of droplets and thus a two-dimensional supersolid. Besides the obvious accomplishment of a feat never before done, the new state of matter opens unimaginable possibilities for research into the unknown. Now, the supersolid form is in a new dimension, from a tiny tube into a small 2D sheet. The fundamental laws of physics are about to get even more fascinating. On his deathbed, German physicist Werner Heisenberg is alleged to have said, "When I meet God, I'm going to ask him 2 questions. Why relativity? And why turbulence?" I really believe he'll have an answer for the first. Whether Heisenberg said that or not, turbulence is everywhere. Any air traveler knows its effects on aircraft. You can see it as water flows over and around rocks, and your body circulates blood and nutrients through a convoluted and turbulent system. But equations used to describe realistic conditions of turbulence rapidly disintegrate into an unstable and tangled mess. Think weather forecasting. To accurately analyze and measure turbulence, that is, to form a general theoretical description of it, has been an elusive white whale of science for centuries. With the advent of two-dimensional supersolids, scientists can now study how vortices form in the hole between several adjacent droplets, and thus advance our understanding of intricate interactions on a quantum scale, and maybe, just maybe, inch closer to unraveling what some call the last great outstanding problem of classical physics, and quantum technologies of which we can barely imagine just took a major step forward. So what do you think about this new state of matter and its limitless possibilities? Are we about to witness advances that were inconceivable of